This is the Chapter 6 pre-class lecture on fossil fuels, electricity, and power plant efficiency. So the picture shown here is a schematic of a typical power plant, and to be specific, a fossil fuel burning power plant. And so you have a series of energy conversions that takes place. The first law of thermodynamics states that energy is not created nor destroyed, but just simply converted or transformed from one form into another form. And then the second law of thermodynamics also holds true for a fossil fuel burning power plant. Another thermodynamic property, in addition to energy changes and transformations, is entropy, which is a measure of the amount of disorder or randomness of the universe. And the second law says the entropy or randomness of the universe is increasing. And so the types of energy conversions that take place in a typical power plant, well, you first have to burn the fuel in order to release the energy in the bonds of those fuels. So we've already talked about and looked at a particular combustion reaction in the previous video, where we calculated the amount of heat, the delta H of combustion, that gets released as a result of the bonds breaking in the reactants and the bonds forming in the products. Adding those bond energies together, with the bond forming, of course, being exothermic, the bond breaking being endothermic, adding those two results together to give you the overall delta H of the reaction. And so therefore, the potential energy that's stored in the bonds of the fuel, which is our main reactant, that is stored chemical potential energy in those fuel molecules. Well, that stored chemical potential energy in those fuel molecules, when it's placed in the burner and combusted, that stored chemical potential energy is converted into kinetic energy. So how is that true? Well, taking a look at the schematic of the power plant, what you have in the burner is your fuel. Let's say we're burning coal. In our power plant. And then the flames there. There's our ignition source to combust the coal. And sitting above the burner is a boiler that has water in it. And that is liquid water. And so the heat that is released from burning the coal gets transferred to the liquid water. And that causes the liquid water to get converted into water vapor or steam. And that steam moves because it is now water vapor or gas. Remember the beginning of the semester, first chapter, we said that gases have kinetic energy. Gases, those particles are spaced out far apart from each other. They have complete freedom of movement. So the stored chemical potential energy in the fuel, in those bonds holding the fuel molecules together, those bonds get broken, and that energy is transferred to liquid water. That heat transferred to the liquid water converts the liquid water to gas, which we also call water vapor or steam. And then that steam now in gas form can move, and it moves to a turbine. And the kinetic energy in that steam causes the blades of the turbine to move. And so therefore the kinetic energy in the steam gets converted into mechanical energy that causes the blades of the turbine to move. And then the mechanical energy created in the turbine gets transferred to the generator. And the generator converts the mechanical energy into electrical energy. And that is the electricity that is sent to our homes and buildings and so on and so forth. So what happens to this steam that causes the turbine blades to move? Well, that steam is then sent to a condenser where the water vapor gets converted back to liquid, which we call a condensate. And then it gets pumped back into the boiler. It gets recycled, some of it. Well, all of it gets recycled. Some of it is sent back to the boiler. So this amount gets sent back to the boiler. And then other amounts of the condensed warm water, which we call the condensate, because it's very, very warm, it's sent to a large body of water where it can cool off. And then the cooling water is then pumped back into the condenser. So the water that's used, it's recycled. That steam gets condensed back to liquid water. Some of it is sent back to the boiler. The rest of it is sent to a large body of water like a river or a lake. And then cooling water for the condenser is pumped back into the system from that large body of water. Now, not all of the heat that's generated by burning the coal actually gets converted into electricity. No power plant is 100% efficient. So how efficient is a power plant? Well, the net efficiency is going to be equal to the electrical energy produced divided by the heat that is produced from that fuel burning times 100. So taking a look at some questions. Most power plants are about 32 to 37.5% overall efficiency. The maximum theoretical efficient being a function of the highest and lowest temperatures needed to make steam and then condense it is 55 to 65%. But the actual overall efficiency is only about 32 to 37.5% efficient. That means of all the heat that is generated from burning the coal, only about 32 to 37.5% of that heat is actually used to make electricity. The rest of the heat gets lost, not really lost, but just absorbed as you go through each step by step of the power plant process. Some of it gets absorbed by the pipes, so on and so forth. So here again is our picture of our power plant. And the coal, of course, appears in the burner, as we talked about previously. And then we talked about the water loops. We've got the water loop that comes out of the condenser and goes into the large body of water to cool that warm water off. And we have this other water loop in which some of the warm water goes through the condenser, actually gets pumped back into the boiler. So those are your two separate water loops. One of the loops connects the boiler and the turbine together. And the other loop connects to the large body of water that then pumps cooling water back into the condenser. So the loop that connects the boiler and turbine is under pressure. Why does this loop need to be under pressure? Well, the loop that's connected to the boiler is going to be in which the steam coming out of the turbine goes into the condenser and gets condensed back to liquid. So that particular loop is very important to have under pressure in order for the condensing to take place. And that is because the high pressure increases the boiling point of water. And I'm abbreviating boiling point BP. And so therefore you get higher temperature steam. And this increases the efficiency of your power plant. So if you increase the temperature of the steam, you increase the amount of electricity produced, and therefore you're increasing the efficiency of the power plant. And then another reason why this loop is under pressure is, like I stated earlier, to condense or compress the water vapor into liquid water. So those are the two purposes for the high pressure in that loop: to make the steam hotter and therefore be able to produce more electricity, and then to cause that steam to condense. Then part C, we've got another loop in that water system that's bringing water in and out of a lake or a river. Explain why a large body of water is needed. It absorbs the heat from the hot water and basically cools it off. So you want to cool it off before it's sent back to the condenser. You don't want to send hot water back to the condenser because therefore the steam would never get condensed. The water has to be cool in order to cause the steam to condense back to a liquid. The next question, if you have a coal-burning power plant that's generating electricity at a rate of 500 megawatts, 500 megawatts is equivalent to 5 times 10 to the 8 joules per second, because 1 megawatt is 1 million joules per second. That causes the plant to have an overall net efficiency of 37.5% for the conversion of heat into electricity. So we need to calculate the electrical energy or the electricity in joules generated in 1 year of operation and the heat energy used for that purpose. So we need to calculate how much electricity is being generated and how much heat is generated by burning that much coal. Those are the two things we're calculating in this question. So how much electricity is generated? Well, we know that a power plant efficiency is going to be equal to the electrical energy produced divided by the heat from the fuel. Okay. So if we have electricity that's generated is 5 times 10 to the 8 joules per second, and then we also know the efficiency, then we can calculate the heat. And then if we know how many joules per second of electricity that's generated, then we can calculate the amount of electricity generated in an entire year. So first, let's calculate the amount of electricity generated in a year. We know how much is generated in a second. Every second, this many joules. So the question is asking how many joules per year. That's an easy question. You just got to convert seconds to a year. There's 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, 365 days in a year. This will give us joules per year. The next question, how much heat was burnt? How much coal was burnt to generate enough heat, Q, to generate this much electricity in a year? So how much heat did the coal generate to produce 1.58 times 10 to the 16th joules per year of electricity? And so the heat which we call Q is going to be equal to the electrical energy, which we already calculated, This is the electrical energy generated in 1 year. Divided by the percent efficiency. Of course, we got to change that percent to a decimal by dividing by 100. So therefore, our heat Q is equal to 1.58 times 10 to the 16th joules per year, divided by the efficiency, 37.5%, divided by 100 to move that decimal 2 spaces to the left, and you've got 0.375. And so therefore the amount of heat is 4.21 times 10 to the 16th joules per year of heat that needs to be generated by burning coal in order to produce 1.58 times 10 to the 16th joules per year of electrical energy. So that's the amount of heat that needs to be generated in order to produce this much electricity. Part B, assuming that the power plant burns coal and coal releases 30 kilojoules per gram of heat. Calculate the mass of coal in grams and in metric tons that is burned in 1 year of operation. And so your delta H of combustion is going to be equal to your heat Q divided by the mass. So therefore, mass is going to be equal to delta H of combustion. Delta H is going to be equal to Q. I'm sorry. I'm just not feeling too well. Mass is going to be equal to Q divided by the delta H of combustion. So let's calculate our mass in grams, and then we'll convert it to metric tons. So the mass is equal to our Q. Well, we already saw for that in part A. Divided by the delta H of combustion. Well, we see we can't cancel a joule with a kilojoule, so we got to do a conversion step. 1 kilojoule is equivalent to 1,000 joules. Now we can cancel the joules, cancel the kilojoules, and we get our mass in grams per year. 1.40 times 10 to the 12th grams per year of coal has to be burnt in order to generate this much heat. And then convert that to metric tons. 1 times 10 to the 6 grams is equal to 1 metric ton. So therefore, in metric tons, the mass is equal to 1.4 times 10 to the 6 metric tons of coal per year. All you do is take your 1.40 times 10 to the 12th grams per year and convert it to metric tons using the conversion factor written above. The grams cancel, and you get 1.40 times 10 to the 6th metric tons per year. And that brings us to the end of the pre-class lecture on generating electricity and power plant efficiency.